I am Crystal Penner. I am from the University of British Columbia, Vancouver, Canada, and I'm a graduate student at that university. So this study was done in a 0 to 400 MeV neutron beam, but this actually is an extension of a previous study called Characterization of a Terbium-activated Gadolinium Oxysulfide plastic optical fiber sensor in photons and protons, which is going to be presented Wednesday. We did this original study to determine whether this particular type of fiber and scintillator showed any promise as a miniature, waterproof, real-time readout, flexible radiotherapy dosimeter. So on the slide is a schematic of the scintillator that we used. It is not to scale. That detector was made of a 1 millimeter diameter plastic optical fiber. It had a 0.5 millimeter diameter cavity drilled in the end. It was 1 millimeter deep and filled with terbium-activated gadolinium oxysulfide, which I'm going to call, for the rest of this presentation, GADOX, because it's much easier to say. We are able to detect signal from the sensor due to the lattice structure of the atoms. So simply, the way an inorganic scintillator works is when it is struck by ionizing radiation, electrons from the populated valence band absorb energy and jump up into the conduction band, which is higher energy level. Very shortly thereafter, they decay back down to a lower energy level. So that'll be either the valence band, but more likely it'll be those activation sites. And when they decay, they lose that extra energy, and they lose it in the form of a photon. And the photon is guided via the optical fiber to the photodetector, which gives us a signal, and that signal is proportional to how much energy has been deposited in the scintillator. So the original study, the one that this one was an extension of, was conducted partly at the Triumph facility on the 74 MeV Proton Beam line. Sorry. And beams like this one, particle beams, can be and are used for radiotherapy, for cancer therapy. But to do this, they have to be very well characterized. Protons deposit most of their energy in a very narrow range, which must be characterized extremely accurately. The example shown here is the proton depth dose. So it is energy deposition with depth, and it's taken with a diode detector. This particular type of dose deposition is useful for small field treatments and treatments that are close to sensitive tissues, because there's no energy that's deposited beyond that peak. At Triumph, eye melanomas are treated on the 74 MeV beam, and right behind the eye is the optic nerve and the brain. So every effort is taken to spare those tissues. When we tested the GADOX detector, we noticed that there was signal beyond that proton range. And we hadn't seen it with the diode. So the figure in this slide shows the depth dose as a function, which is energy deposition as a function of, it says time, but that is directly proportional to depth. So it's as a function of depth. There are several possibilities as to what could have caused this elevated signal, but because neutrons are a consequence of proton irradiation, we thought maybe it could be protons, and then we thought, can the GADOX even detect, or we thought it could be neutrons. And then we thought, can the GADOX even detect neutrons? So luckily, Triumph also has a neutron beam. And so we designed a test to determine how sensitive, and if it was sensitive, the GADOX was to those neutrons using the Triumph neutron facility, which is also called TNF, and you can see it there in the water tank on the figure. The facility is fed by a 450 MeV proton beam. It's called Beamline 1A. The neutrons are created as the proton beam stops on this aluminum plate. I guess I don't have on the aluminum plate, which is inside a water moderator. When the beam stops on that aluminum plate, by spallation reaction, neutrons from 0 to 400 MeV are created. And the ones that are going in the direction already of this neutron channel are directed towards an accessible field. That field can be accessed by lowering a different plate into and out of it with your sensor attached. So in fact, the field that we can access is on all the time. In order to take our tests, we have to manually lower our sensors in, then raise them back out. So beam on and beam off is raising and lowering. So this is an image of the plate that we use to take the tests. It does have a sensor attached to the middle. As I mentioned before, the whole apparatus is lowered into the field and raised back out. And in this manner, we were able to conduct 4 types of tests using 2 different sensors with different densities. So the first test was a fiber-only test to determine background radiation. So that was with just the fiber. We used 2 sensors with different densities to see if there was a threshold necessary in order to detect the neutrons. We tested 1 sensor for 20 continuous hours. We tested the lower density sensor to see if there was any noticeable radiation damage. And we did a vertical profile with the higher density sensor by attaching the sensor at different points along that vertical line. I'm just going to point at it. So this vertical axis, we attached the sensor at different points along it to make a vertical profile. We had to raise and lower for each individual data point. So at this point, it's really important to mention that we are not actually directly detecting neutrons with the scintillators. What we instead detect is the results of interactions between neutrons and nuclei of other atoms. So what happens is we have these interactions: inelastic scatter, which create gamma radiation, absorption, which also creates gamma radiation, and transmutation, which can create gammas, but also other charged particle radiation. We can detect all of those with the scintillator, just not the neutrons directly. So results. The results shown here are from the fiber-only test. This figure that you see is the signal strength over time as we lower the fiber into the field and then raise it out again. And you are wondering about those 2 spikes. So when we set the cable or for the fiber to take the test, we attached the sensor below the field. So when we lowered the plate into the beam, we actually lowered the sensor through the field. That's the first spike. Then we were able to test the cable, which is that plateau in the middle. And then when we raised the plate back out of the field, we raised the sensor back through the field and got the second spike. So the results of that test were, in fact, that we only got a 1.2% increase in signal, which is very low. So we could be pretty sure that what we were seeing was the results of neutrons when we put the scintillator in the field. Now the higher density sensor showed nearly double the signal of the lower density sensor, but both of them had a very good signal. So we were unable to establish any kind of a threshold for the volume of scintillator necessary for detecting neutrons. We left the lower density sensor in the beam for 20 hours, and we saw no significant change in signal strength. So from that, we could conclude there was no significant radiation damage to either the plastic or the scintillator, which was good news. So here we have the results for the vertical profile. This graph shows the normalized signal strength of the scintillator as a function of position. Like I said, up the middle axis. The results for the scintillator are in black, and we compared them to the results from an SRAM, which are in blue. And what we found was that the 2 profiles were roughly similar, but the Gadox showed a narrower profile. Now, the SRAM detects neutrons directly, but it doesn't detect gammas at all. And in fact, gamma radiation is created all through the channel that directs the neutrons into this accessible beam. So the scintillator detector is going to detect those gammas, and the SRAM is not going to detect them. And that could be the reason why we have this discrepancy between the two results. All right, so in conclusion, GADOX does sense neutron radiation. The sensor is able to remain in the neutron field for 20 hours with no observable damage. The vertical profiles of the GADOX and the SRAM are roughly in agreement, though the GADOX does have that narrower profile, and it would warrant further testing. In the future, it would be nice to be able to determine the response of the sensor as a function of the neutron energy, because this neutron energy was from 0 to 400 MeV, which is a very large range. And that concludes my presentation. Thank you all very much. Are there any questions?